Welcome to online class of B.Sc 6th semester. In the last class that we discussed Raman scattering, in which we have studied the different types of scattering such as coherent scattering and incoherent scattering. And also we discussed in detail what is Raman scattering, what are Raman lines, the characteristics of the Raman lines, as well as the experimental arrangement to determine the Raman spectra. And also, in detail, we explained the quantum mechanical treatment of this Raman scattering or Raman effect. Today, we shall discuss with the classical theory of Raman effect. The classical theory of Raman effect is also called as polarizability theory. It was developed by G. Plachik in 1934. As you know, the vibrational spectroscopy or IR spectroscopy is called as is obtained that arises due to the change in the permanent dipole moment of the molecule. That means the molecules which possess a dipole moment, so due to the interaction of the electromagnetic radiation, there is a change in the dipole moment of that molecule that causes the vibrational spectra. Whereas the Raman effect is completely different. The molecules which do not have a permanent dipole moment, such as homonuclear atoms, for example, hydrogen gas, nitrogen gas, so they do not possess any permanent dipole moment. Therefore, the Raman effect is used to determine the structure and components that are present in the molecule in case of homonuclear compounds. There will be change in the polarizability of the substance due to the interaction of that electromagnetic radiation with the molecule. What happens? The positive charge is displaced from the center of gravity of a negative charge. So that is the nuclei and electrons are displaced. It produces the induced dipole moment mu, and the molecule is said to be polarized. So that means due to the interaction of the electromagnetic radiation, it produces the induced dipole moment in the homopolar homopolar nucleus molecules. Okay. Therefore, if E is the strength of the electric field and mu is the magnitude of the induced dipole moment, then this induced electric dipole moment mu is directly proportional to the intensity, that is intensity of the electric field of the electromagnetic wave. So therefore we can write that induced dipole moment mu is directly proportional to the electric field, or mu is equal to alpha into E, where alpha is called as polarizability constant and alpha is called polarizability of the molecule. When a molecule which can be polarized is undergoing a beam of radiation of frequency nu, the electric field E experienced by each molecule varies according to the following equation. Therefore, the electric field E is given by E naught sine 2 pi nu t, where nu is the frequency of radiation and E naught is the maximum electric field of the electromagnetic radiation. And the induced dipole moment mu is given from that equation number 1 and 2. We have mu is equal to alpha into E. In place of E, substitute the value of E from that equation number 2. Hence, that equation number 3 that gives the induced dipole moment, that is equal to alpha into E naught into sine 2 pi nu t. The molecule now behaves like a Hertzian oscillator. The dipole moment mu of an oscillator emits radiation of its own frequency nu. Then equation number 3 explains the Rayleigh scattering. Now the molecule has an internal motion, namely the vibration and rotation. As a result of these motions, the polarizability of the molecule varies. So we shall discuss how this polarizability of the molecule varies with the vibrations of the atoms of the molecule. So consider a change in the polarizability due to vibration. When a molecule undergoing vibratory motion, it changes the polarizability alpha periodically, and thus the oscillation dipole moment will have superposed upon the vibration and oscillation. If the vibrational frequency is V nu V changes the polarizability, then we have alpha is equal to alpha naught plus beta into sine 2 pi nu V into T, where alpha naught and beta are constants, where alpha naught is the value of polarizability in equilibrium position and beta is the maximum change in the polarizability during vibration. Substitute the value of alpha is equal to alpha naught plus beta into sine into 2 pi into nu v into t in equation number 3. We have alpha is equal to mu is equal to alpha into e, and that is equal to alpha naught plus beta into sine into 2 times nu v into t, then E naught sine 2 pi nu t. So on simplification, this equation, okay, and also using the trigonometric relation, finally we arrive at the equation that is 5, so which contains the 3 terms. The 3 terms are the first term, so that constitutes the Rayleigh line, and second and third, they constitutes the Stokes and anti-Stokes line. The middle term 1 by 2 beta E naught into cos 2 pi t into nu minus nu v, that means the frequency is decreased. Once the frequency is decreased, so its wavelength increases, so this middle term that corresponds to Stokes line. And next 1 by 2 b into E naught into cos 2 pi t into bracket nu plus nu v. So that means the final frequency of vibration, that is of scattering light, has the higher frequency than the incident radiation frequency. Therefore, its wavelength decreases. So that corresponds to anti-Stokes line. So from this equation number 5, it is clear that the induced dipole moment oscillations with frequency components nu, nu minus nu v and nu plus nu v, which are almost same as that of the incident radiation, it depicts Raman effect. So the Raman shift is given by, that is Raman shift, that is delta nu, that is equal to nu plus nu v minus nu, so that is equal to nu v. From the equation number 6, it is clear that the Raman shift would be equal to the vibration of the frequency nu of the molecule. That is, that gives the vibrational oscillation of the, that is vibrational frequency of the that molecule. Next, what is the effect of rotation? Because the molecules are rotating, the atoms of the molecule are rotating about a fixed axis. Due to that rotation, there is a change in the polarizability of the molecule. So, how it changes the polarizability of the molecule and what is the corresponding change or shift in the Raman lines that we can observe. So, let us consider a change in the polarizability due to rotation. When a diatomic molecule rotates, the orientation of the molecule varies with respect to the electric field of rotation. If the molecule is not optically isotropic, it has different polarizabilities with the time. Then the equation number 4 will be, that is alpha is equal to alpha naught beta sine 2 pi nu r into t, or alpha is equal to alpha naught plus beta dash sine 2 pi nu r into t, where nu r is the frequency of rotation and beta dash is the change in the polarizability due to the rotation about an axis. As the molecule rotates, the polarizability is same for opposite direction of the applied field, and beta dash changes at twice the rotational frequency nu r. The expression for the induced dipole moment becomes, so that is nu, that is equal to alpha into E, so that is equal to alpha into E naught sine 2 pi nu t. So therefore alpha is equal to alpha naught plus beta dash 2 pi t into 2 times nu r. Substituting the value of alpha in the equation number 3 and on simplification and using the trigonometric relation, we finally arrive at equation number 8. So that is mu is equal to alpha naught E naught sine 2 pi nu r into t plus 1 by 2 nu t plus 1 by 2 beta into E naught into bracket cos 2 pi t into bracket nu minus 2 times nu r minus cos 2 pi t nu plus 2 times nu r. It is not nu v, it is nu r. That is rotation. R stands for rotation. Again, from equation number 8, it is clear that the induced dipole moment of oscillations with the frequency components, that is nu, the first one, which is Rayleigh line, and nu minus 2 times nu r, so that is decrease in the frequency, increase in the wavelength, corresponds to Stokes line, and nu plus 2 times nu r, increase in the frequency, decrease in the wavelength, corresponds to anti-Stokes line, which are almost same as that of the incident radiation. It depicts Raman effect. So the Raman shift is given by Raman shift, that is delta nu, that is equal to nu plus 2 times nu r minus nu, and that is equal to 2 times nu r. So from equation number 9, it is clear that Raman shift would be equal to twice the frequency of rotation of the molecule. From the above, it is clear that the induced dipole moment changes not only with the frequency nu of radiation of the light, but also with the frequencies nu minus nu v, nu plus nu v, nu minus 2 times nu r, and nu plus 2 times nu r. Hence, in the spectrum of the scattered light, one obtain the vibrational Raman lines at a distance of nu v on either side of nu, and it is thus clear that molecule need not have a permanent dipole moment for its Raman spectrum to appear. The significance of the Raman effect. The infrared absorption spectra of a molecule, both vibrational and rotational, can be analyzed with the help of Raman spectra. By shifting to the visible part of the spectra in any convenient position, Raman spectra contain even those lines of the infrared absorption spectrum which are forbidden in the direct study. Homonuclear molecules like H2, which do not exhibit vibrational and rotational spectra directly, exhibit the same in a Raman shift. The most important applications of Raman effect, so that is to in physics, the Raman effect has been put to a very great use in the study of molecular structure. So that means analysis of Raman spectrum of diatomic and triatomic molecule. For example, diatomic molecules like hydrogen gas, deuterium gas, nitrogen gas, oxygen gas, then HCl, HBr, and HI. And triatomic molecules like carbon dioxide, water, and N2O. It also helps the study of Bernoulli's theorem, okay, and it also helps to provide information about the binding forces in the crystals. The nuclear physics, in case of nuclear physics, study of certain aspects of nuclear physics such as spin statics as well as the spin statics and as well as the isotopic constitution of the nucleus. In chemistry also, the Raman effect is has a very wide applications. The application of Raman effect in chemistry in all its three different branches, so that is inorganic, organic, and physical. In case of inorganic chemistry, the chemical constitution and valence bond can be determined. In organic chemistry, the Raman effect has found to a great value of organic chemistry. It has been used to determine the presence and absence of a specific linkage in a molecule, identifying the impurities of the certain types, study of different types of isomerism, various chemical effects such as electrolytic dissociation, hydrolysis, strength of the that bonding, all these can be determined with the help of this Raman spectra. So we shall today we shall go through certain problems on this Raman effect. So the first problem, that a radiation of wavelength 546.1 nanometer excites a substance to emit a Raman line of wavelength 538.2 nanometer. Calculate the Raman frequency and the wavelength of the corresponding Stokes line. The wavelength of the incident radiation, that is given lambda I, that is equal to 546.1 nanometer, or that is equal to 546.1 into 10 raised to minus 9 meter. The frequency of incident radiation nu I, okay, so that is given by, that is C by lambda I. So C is 3 into 10 raised to 8 divided by that lambda I. So that works out to be 5.493 into 10 raised to 14 hertz. The frequency of Raman line, that is nu R, that is equal to C by lambda R, and substitute the values of lambda R and C, you will get 5.557 into 10 raised to 14 hertz. Therefore, the shift in the Raman frequency, so that is equal to delta nu, that is equal to nu I, the difference in the incident radiation frequency and the frequency of the scattered radiation. So that is nu I difference nu R. So on taking the difference between these two, the frequency of the Stokes line, because there is a nu I that is less than nu R, that is increase in the frequency, that corresponds to decrease in the wavelength, that corresponds to Stokes line. So nu S, that is equal to 5.493 into 10 raised to 14 minus 0.081 into 10 raised to 14, okay. So that becomes 5.1412 into 10 raised to 14 hertz. So wavelength of the Stokes line, that is lambda s, so that is equal to C by nu. So that was out to be 5.543 into 10 raised to minus 7 meter, or 554.3 nanometer. The second example, in an experiment on the study of Raman effect using mercury green radiation of wavelength 546.1 nanometer, a Raman line of wavelength 554.3 nanometer was observed. Find the frequency and wavelength of the Stokes and anti-Stokes line. You have to go in the same manner that you have solved in the problem number 1 and determine the frequency of the Stokes line. So that means we will, that is first you have to find out the Raman shift. With the help of Raman shift, so that is original wave frequency minus the Raman shift, that gives the frequency of the Stokes line. From that you can determine the wavelength of the Stokes line, that is 554.3 nanometer, and the frequency of the anti-Stokes line that is obtained, that is original frequency plus the Raman shift frequency. So that works out to be 5.624 into 10 raised to 14 hertz, and lambda of the anti-Stokes line, that is wavelength of the anti-Stokes line, so that is 531.7 nanometer. And in the third problem, in a Raman spectrum, wavelength of incident light is 589 nanometer and wavelength of the Stokes line is 600 nanometer. Calculate the Raman shift in hertz. The wavelength of the incident radiation is 589 into 10 raised to minus 9 meter. The frequency of incident radiation, that is nu I, that is equal to C by lambda I. So that was out to be 5.093 into 10 raised to 14 hertz. The frequency of the Stokes line, that is nu S, that is equal to 3 into 10 raised to 8 divided by 600 into 10 raised to minus 9. So that works out to be 5 into 10 raised to 14 hertz. Therefore, Raman shift delta nu, that is equal to nu I difference nu R. Here nu R, that is nu S, that is Stokes line frequency. So that is less than this incident vibration. So 5.093 into 10 raised to 14 minus 5. So that also to be 0.093 into 10 raised to 14 hertz. So that is the Raman shift. And the fourth problem, when excited with the radiation of wavelength 546.1 nanometer, a substance showed a Raman line at wavelength 554.3. Calculate the frequency and wavelength of the corresponding anti-Stokes line. So you have to go in the same manner, that is wavelength of the incident radiation is given. From that you can calculate the frequency of the exciting radiation, which works out to be 5.493 into 10 raised to 14 hertz. The frequency of the Raman line, that is nu R, that is equal to C by lambda R. So that was out to be 5.412 into 10 raised to 14 hertz. Therefore, Raman frequency delta nu, that is equal to nu I difference nu R. Here nu R is 5.412, whereas nu I is 5.493. Therefore, 5.493 minus 5.412, that was out to be 0.081 into 10 raised to 14 hertz. So that is the Raman frequency. So that we are determining. So totally there are 4 solved problems that I have discussed. If you have any problems in solving the problems or difficulty in solving the problems, you can anytime you can discuss with me. So with this I conclude the Raman spectroscopy. Thank you.